gases and liquids are fluids since they don't maintain a fixed shape. Density is shown by the Greek character rho, and it's mass per unit volume. Density equals mass over volume, and it's measured in kilograms per meters cubed. And if density is given in grams per centimeters cubed multiplied by 1,000, you get kilograms per meters cubed. Pressure is force per unit area. Force acts perpendicular to the surface area A. Pressure equals force over area. Pressure is measured in newtons per meters squared, which is Pascal. And 1 Pascal equals 1 Newton per meter squared. A fluid exerts pressure in all directions, and pressure varies with depth. Pressure variation with depth is found by using the equation pressure equals rho times gravity times h. The atmosphere exerts a pressure equal to 1.013 times 10 to the 5th pascals, and gauge pressure measures pressure above atmospheric pressure. Pascal's principle states that the pressure applied to a confined fluid increases the pressure throughout by the same amount, so pressure in equals pressure out, and this is used with hydraulic lifts. They have a smaller area. When they put a force on that, it will go to a larger area, and they're able to lift cars through that with a greater force.
Buoyancy. Fluids exert a buoyant force upwards on an object because of a difference of pressure at the top of the object and the bottom of the object. So, at the top of the object there's going to be less pressure than there is at the bottom, because at the bottom of the object it's at a greater depth, which creates more pressure. The buoyant force is equal to the weight of the fluid displaced, which can be found by doing the density of the fluid times gravity times the volume of the object, or the volume of the fluid displaced. When an object floats, the buoyant force is equal to the weight of the object. The fraction of the object submerged is equal to the ratio of the object's density to the density of the fluid. The equation of continuity. Since a liquid is incompressible, the volume of a liquid moved through a pipe is constant. The velocity of the fluid can be found using A1 V1 equals A2 V2, and AV is the volume rate of flow, which is equal to delta V over delta T, and when you solve it, it equals AV. Bernoulli's equation. Bernoulli's principle says that where the velocity of a fluid is high, the pressure is low, and where the velocity is low, the pressure is high. Here's Bernoulli's equation. P plus rho GY1 plus 1/2 rho V squared is a constant throughout a fluid. P is the external pressure, so atmospheric pressure and anything above. A lot of times you can cancel those out if there's atmospheric pressure on both sides of a system. The velocity can be set to 0 in many cases, so if the fluid is escaping through a small hole in like a large dam or a large cup, then the velocity at the top of the fluid can technically be considered 0, so you can just cancel out the 1/2 rho V squared.
A beaker weighing 2 newtons is filled with 5 times 10 to the negative third cubic meters of water. A rubber ball weighing 3 newtons is held entirely underwater by a massless string attached to the bottom of the beaker, as represented in the figure above. The tension in the string is 4 newtons. The water fills the beaker to a depth of 0.2 meters. Water has a density of 1,000 kilograms per meters cubed. The effects of atmospheric pressure may be neglected. Part A. Calculate the weight of the entire apparatus.
So, we know the weight of the beaker, in this case, is equal to 2 newtons, and it was also given that the weight of the ball is 3 newtons. So, we have to find the weight of the water inside the beaker. And so we're going to start by finding the mass of the water, and now mass equals rho times volume. So the mass of the water is going to equal the density of the water, which is 1,000 kilograms per meter cubed, times the volume, which is 5 times 10 to the negative third meters cubed. So the mass of the water comes out to be 5 kilograms. Now we need the weight of the water, so we multiply 5 by 9.8 to get 49 newtons, and that's the weight of the water inside the beaker. So to find the total weight, we add 2 plus 3 plus 49, and you get 54 newtons as your weight for the entire system.
Part B. On the dot below that represents the ball, draw and label the forces, not components, that act on the ball.
So we know that the ball is attached to a string and we know that it's underwater. Now first, we know that there's the weight of the ball, which is equal to mg, which points downwards. Next, because of the string, there's a force of tension, which also points downwards. And finally, because the ball is underwater, there's a buoyant force, which points in the upwards direction.
Part C. Calculate the buoyant force exerted on the ball by the water.
To find the buoyant force acting on the ball, we have to refer to our force diagram from Part B, and we also have to utilize Newton's second law, which states that the sum of the forces equals mass times acceleration. Now we know from the fact that the ball is not moving that acceleration is equal to 0, so we can write that the net force is also equal to 0. Next, we write out all of the forces acting on the ball, and we write that the buoyant force minus the tension minus the weight all equals 0. Next, we fill in the values for the tension, which is 4 newtons, and the weight, which is 3 newtons. And then we add 4 and 3 to both sides, and we get that the buoyant force is equal to 7 newtons.
Part D. Calculate the pressure due to the liquid at the bottom of the beaker.
To find the pressure at the bottom of the beaker, we have to use the equation pressure equals rho g h, where h is the distance underneath the surface of the water. So pressure equals rho, which is 1,000 kilograms per meter cubed, times g, which is 9.8, times h, which we are given in the problem to be 0.2 meters. And when you calculate that, you get 1,960 pascals.
Part E. The string is cut and the ball rises to the surface and floats. Indicate whether the water level is higher, lower, or the same after equilibrium is reached.
If the ball rises to the surface and floats, then we know it displaces less water than it did when it was completely submerged. Therefore, the overall level of water in the beaker would have to be lower than it was when the ball was completely submerged. The following is a demonstration of Pascal's principle, which states that pressure in equals pressure out. The force exerted on the surface area at the top of the bottle is proportional to the force exerted on the bottom of the bottle, but the force at the bottom is enough to cause the bottom to break away cleanly. You should only attempt this demo if you are a trained professional. Do not try this at home.
You used to call me paranoid, pressure, but even you cannot avoid pressure.
They use the do you know what I'm talking about? Hydraulic lifts.
Yes, like you apply a force to an area that's
On a
smaller,
small one,
and then on the
it's
opposite
able
side
to
that
lift
force.
through.
Right here? Okay.
You're really cut off.
Duck down.
Wait, what do you mean?
Like your head's cut off.
Like,
Really?
Yeah, duck down a little bit. There you go. You're good.
Can you tell that I'm...
No, you really can't.
Are you sure?
Yeah.
I can't.
What if I forget and I lift myself
Go!
back
Stop
up?
it! Don't do that.
Okay, thank you.
At least we'll have bloopers.
Rho VG when an object floats. I don't like you. When an object floats, the buoyant force is equal to...
Why are you laughing?
Wait, when it floats... Can you see my face? Buoyancy continued. The buoyant force, again, is equal to the weight of the... Did I ever say that? I don't think I ever said that.
Buoyancy continued.
So now here's some new stuff.
Excuse.
Are you gonna do it?
Are you gonna
Excuse me. I don't even know what to do.
Excuse
me.
Excuse me.
just cry?
I'll just walk out.
Your wife is dead.
You made a huge mistake.
Why do I have to be tall? And you guys are like little midgets. Safety gear. Wow.
I was trying to get out of the way.
I was trying to get out of the way too.
Wait, no, we're not doing this. It's gonna fall right in. Yeah, we'll throw the ball back.
That's not a good idea.
You don't even have to be in it. It's just a ball.
Oh,
That could have been so much worse. We should just put a clip of Job at the end of our bloopers that says I've made a huge mistake. Can we do that?
I've made a huge mistake. I've made a huge mistake.